Day 76, Honors Physics, Universal Gravity, Problem 26. Conceptually, this might want to be, it's probably one of the more difficult problems we've done this year. So let me explain a little bit here. So we have the Earth and the Moon, not to scale. Separated center to center, the distance down here, 3.85 times 10 to the 8th meters, that's given. That's how far apart it is center to center from Earth to Moon. Now, if you put a spaceship right here, I have a blue dot, or the red marker, it's being pulled towards the Earth because of the gravitational force of the Earth, and it's being pulled towards the Moon. What they want to know in this problem is where's the location such that the forces will be equal to each other and cancel, so in a sense, they'll be kind of stuck there. Well, we know that this location right here has to be closer to the Moon because the Earth, by virtue of its size, exerts a greater force. But the force is also dependent on your distance. The closer you are to an object, the stronger that force is. So we know we have a location here closer to the Moon so that this force is big enough to cancel out this force, to give you an F net of 0. What I'm doing now is calling the distance from the Earth, the center of the Earth, to this spot, I'm calling that x. I could have called it r sub 1. But it's a distance from Earth to this location. And from the moon, center of the Moon to this location, I'm calling it y. But I've really kind of done a little overkill there. I really don't need the variable y. I'll use it for now. Because I know that, in other words, x plus y equals this, whole distance. Or in other words, if I know the whole distance, which I actually do, what I don't know is x and y, but if I take the whole distance minus x, that will equal to y. For example, if the whole distance were 10 meters and x were 7, then y would be 3, because x plus y has to equal the whole distance. The fact that this number is big and it's in scientific notation causes a little bit of confusion. But x plus y equals the whole distance. Now, I'm looking for location, going back up over here to the right now, where the force that the Earth exerts on the satellite equals the force the Moon exerts on the satellite. Right? The universal equation is gmm over r squared. I'm using x for my r because that's my specific distance from the Earth to this location I'm looking for. So it's g mass of Earth times the mass of the satellite, the little mass at that blue dot, over the distance squared, gmm over r squared. Same thing for the Moon now. It's g times the mass of the Moon times the mass of that satellite or spaceship or any object over y squared, how far I am from the Moon. Now, you can save yourself a lot of anguish by doing some nifty little algebra tricks here. Not really tricks, but save yourself some time. For example, if you look at this, there's no addition or subtraction. There's just two terms or factors on both sides. In other words, the g's will cancel, and the m's will cancel. So on first swipe here, you can have mass of Earth over the distance to the Earth squared equals mass of Moon over the distance to the Moon squared. Now the squaring would be problematic here because I need to get rid of the y. I'm going to plug in here for the y in a second. To get rid of the y, I'm going to plug in this on the left here. I'm going to plug that in for y. So I'll have only one unknown because we're going to assume that we know the mass of the Earth and the mass of the Moon, which we do. I'll write those down. Actually, they're on your sheet. Actually, the mass of the Earth is on there. I'll give you the mass of the Moon as well. Those are known values. So the only unknown is going to be x. But before we do that, here's the main trick here. Take the square root of both sides. If I take the square root of both sides, I can show you that symbolically. You don't need to do that. You can probably do it in your head. But square root of this side, square root of that side. Bottom line is, what you end up with is the square root of the mass of the Earth divided by x equals the square root of the mass of the Moon divided by y. So I've gotten rid of those pesky squares because what's going to happen here is I'm going to get a binomial for y here in a second. I don't want to square a binomial. You've got to use the FOIL method and the quadratic formula possibly. I want to try to avoid that, which I am now going to be able to do. All right, so let me pause for a second and write down my data. Okay, so there's my data. Basically, everything over here in the red circles, I'm going to be plugging in. I know the mass of the Earth, the mass of the Moon, so those are going to be plugged in, numerator. And I'm going to take this 3.85, I'm going to crisscross here, I'm going to plug that in for y. So all I'll have is the square root of some big numbers. You can take the square root of those numbers and get numbers without square roots, obviously. And then you'll cross multiply, distributing this here, which will be a number that's the square root of the mass of the Earth, times a binomial. And don't forget that you're going to have to multiply by each of these two terms. So let's see if you can do the algebra on that. Plug those numbers in, solve for x. That'll tell you how far from Earth you'll need to be to satisfy the conditions in the problem. You can also figure out then, plug in for x to, in this equation right here, once you have x, to see how far you are from the Moon. So, good luck. If you have questions, you can ask me in class.